We're going to continue talking about the periodic table today. You have an indication already of the way in which it's arranged. We want to finish talking about our main group elements today, get into the transition elements, and then we'll get into periodic trends, which is the trickiest but funnest part next time. So your learning goal is listed. You've seen this several times already, and we are going to continue talking about the different families or groups of elements. We do want to review what we did the other day, and if you were out and missed the lesson, make sure you watch the videotape, although I'm pretty sure most of you were here. If we look at a periodic table shown here, you will recall that main group elements are in which two blocks? The S block and the P block. So main group elements are in the S block and the P block. And group 1 is known as the alkaline metals. When you react group 1 elements with water, they generate alkaline solutions in hydrogen gas, and you get that explosive reaction. Group 2 are known as what? Alkaline earth metals. And then the first column here in the P block is the aluminum family. We're going to continue with our main group of representative elements today, the carbon family, the pnictogen family, the chalcogen family, the halogens, and the noble gases. And then we'll close with a brief overview of the transition elements as well as the inner transition elements, which are not main group elements. So your main group elements are the S and the P block. And remember, these end in S1, group 2 ends in S2, group 13 ends in P1, then P2, etc. The other thing we started to allude to, and you'll see this in this table I recommended that you work through, definitely do by Wednesday, should be very easy for you, is for your main group or representative elements, if you're looking at the number of valence electrons, remember valence electrons are electrons in the outermost shell, S and P only. Groups 1 and 2 have 1 and 2 valence electrons respectively. The P block, which consists of groups 13 through groups 18, their valence number of valence electrons will be the back digit of the group number. So group 13 has 3 valence electrons, as we talked about the other day. Group 14, 4, group 15, 5, etc. And we'll point that out as we go. So we're going to pick up with the carbon family. That's where we left off the other day. And with the carbon family, you're going to see a family of very different elements. You've got a non-metal, metalloids, and metals in the carbon family. If we look at the carbon family, you have a non-metal, 2 metalloids, and metals. These are some of the newer elements that have recently been synthesized in the laboratory. Let's take a look at the electron configuration. The other day we labeled our periodic tables so that we could work off of them to write electron configuration. If you weren't here, I labeled off a few in class, and I'm happy to give you one of mine. But you should be able to, with practice, write electron configurations from the periodic table alone, where you wouldn't need the subshell tree diagram. So work with those now, and let's try and work through group 14. So in group 14, we've got carbon, silicon, germanium, tin, and lead. And if we consider the electron configuration in shorthand, these are going to end in NS2, NP2, for 2 plus 2 will be 4 valence electrons. Raise your hand if you're struggling with shorthand, because we can work on it together now. All right, Bryson, you're up first. I'm going to help you. You ready? I'm going to flip this like this. So carbon, I'm going to help you with the first, and you're going to help me with the second. When you write the electron config for carbon, right here, you go all the way across and up one, and you put that noble gas, which is helium, in brackets. Then carbon is in the second row or period, so the number after the brackets is 2. If you were here, you'd have 2s1. If you were here, you'd have 2s2. If you're past this, you keep going. So S2, and then back to 2, P, this would be 1, this would be 2. So carbon is helium 2s2, 2p2. Okay? Now you're going to help me with the next one, which is silicon. What is the noble gas that comes before silicon? Say it again. Yes, neon, exactly. You went all the way across and up one. And now silicon is in what period? Third is correct. It's not in the S block, so you fill that up. And after 3S comes 3P. And it's in the second column of the P block. And that's your electron configuration. Highest value of N is 3, 2 plus 2, 4 valence electrons for group 14 elements. Okay? A little trickier in the 4th and 5th period, which you'll see here. So we're going to do germanium and tin. For germanium, we're going to go all the way across and up one, which is argon. Germanium's in the 4th period, not in the S block, so I'm going to fill up that S with 2. Now before I get to the P, I have to go through this whole midsection. And this midsection right here is the D block. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in a period of the D block. In addition, in any D-containing subshell, how many electrons can those D orbitals hold? 10. The number before D is 1 less than the row you're in. So you have 3D10. Again, the number before D is 1 less than the row you're in. After D, we go back to the row number and P, and we get 4P2. And again, highest value of N, S and P electrons only, 4 valence electrons. Raise your hand to do tin. Go ahead, Halen. Tin, SN.
So maybe krypton.
Okay.
And then.
Probably better off in the periodic table off your thing. Here, do you want to, hang on one sec. Let's try this. Here, no, this might be easier. Here's tin.
Okay, yeah, that's easier.
Let me put the orbital things in. All right, here's tin. All the way across up one is krypton. Now you want to get back here. What period are you in?
5.
5. And you go through S, so you have 5s2, then what?
4D10,
And then
and then, oh.
back to the row. 5,
Oh, 5
P.
5P, 2.
5P2 is correct.
Okay.
Just like that. Go ahead, Will.
You said something. You said you add the S and the P electrons to get the valence electrons.
Of the highest value of N. So like on this one that we're doing now, the highest value of N is the row the element's in, which is the 5th, and then the 2 and the 2 make 4 valence electrons. Yes, yes? D electrons are not valence electrons. In addition, these are in what shell? Look right here. The D electrons here are in what shell? Right. So they're not the valence ones. They're not in the outermost shell. The outermost shell is the 5th one, the row you're in. All right, the last one's the trickiest of the bunch with lead. And let's take a look here. With lead, we've got right here. What's the noble gas that comes before lead? Xenon. Lead is in what row or period? 6. So we're going to do 6s2. Now look right here. A whole bunch of elements have been pulled out. Now this is a little confusing because lanthanum is right here, and then the other 14 elements would be right where the dot is. So you actually can put them in. Watch. Don't miss it. But now the periodic table gets wicked long. But what you can see here is here's lead, all the way across up 1 is xenon, 6s2, the number before F is 2 less than the row you're in, 4f14, 5d10, 6p2. Let's get that down on paper. So lead is xenon, 6s2, 4f14, 5d10, 6p2. And again, the highest value of N is the row the elements located in. The S and P electrons make up the valence electrons for 4. The number before F is 2 less than the row you're in. The number before D is 1 less than the row you're in. All right? And we won't do this for every single element in every group because you guys are going to get bored. But most importantly, can you write shorthand electron configs? If you can write them from the periodic table only, that's great. If you need your subshell tree diagram at this stage of the game, that's fine too. But you have to be able to write shorthand for the next quiz. All right? I don't know how to go back. And if I do that, it's going to disappear.
I just press the arrow next to English on the bottom, and then.
No, it's we don't want wide. I think that's it. Is that what you're saying to me?
No, like put it back to the.
No, I forgot. I have to hit the wide thing because now I'm not a wide body like a wide body airplane. Alrighty. In group 14, what's also very interesting is in chemistry, atoms will lose, gain, or share electrons to have an octet of electrons in their outermost shell. Typically, if you have fewer than 4 electrons in your valence shell, if you have fewer than 4 valence electrons, atoms tend to lose. If you have 5 or more valence electrons, they tend to gain to get to 8. 4 is that dividing line. So in group 14, the carbon family, the atoms can lose 4, they can gain 4, or very often, especially in the case of carbon, they will share 4 electrons with other atoms to complete that octet of electrons. And they will form covalent compounds. For example, in the next chapter after this, so 2 chapters from now, you're going to learn how to draw compounds. Carbon dioxide is a covalent compound, and you will see that carbon will share 4 electrons to complete its octet. So this is a covalent compound. Other covalent compounds include methane. This is the gas that you release. Propane is another gas. Many of you have propane tanks hooked to your grills outside. What's interesting about propane, as well as many other compounds, is the carbon atoms form chains. And you see this with fats and oils as well. You get these long chains of carbons. In some of your sugars like glucose, you get rings of carbons. And this is known as concatemerization. Not really that critical here. But carbon especially is one of those atoms that tends to share electrons. And in the carbon family, what you're going to find is everything, a nonmetal, 2 metalloids, and 2 metals. So you have a little of everything. The next family is group 15, nitrogen, phosphorus, arsenic, antimony, and bismuth. And this is your pnictogen or nitrogen family. Sorry.
The carbon family, is the sharing, does that make an ion?
No.
What does that make?
It makes a covalent compound. So with ions, when you lose electrons, you're a cation. When you gain electrons, you're an anion, as we talked about in chapter 2. Those are going to form ionic compounds. So you don't find that many with carbon. You can find carbides, which are very strong. But toward the bottom of the group, for example, you have lead. And this is lead 4 chloride. And this is going to be an ionic compound. And that's an ionic compound that's comprised of lead 4 ion and 4 chloride ions. In a covalent compound such as carbon dioxide or either of these, what you get are these bonds. These are covalent molecules. You have covalent bonds formed through the sharing of electrons. And we'll talk about that in chapter 6, and we'll learn how to name the compounds and draw them and shapes and all kinds of fun stuff. Alrighty? But yeah, this will be an ionic compound. Ionic compounds are between metals and nonmetals. Covalent compounds are between 2 or more nonmetals that share electrons. And we'll talk about that in some detail in chapters 5 and 6. And then I've got an easy project for you to do at home so that you really understand the difference between ionic compounds and covalent compounds. And you wouldn't believe what's in some of the food that you eat. Healthy food and not so healthy food. All right, so group 15 is your pnictogen or nitrogen family. And this is a funny little name. Sometimes the kids confuse. And your pnictogen or nitrogen family consists of nitrogen, phosphorus, arsenic, this is in poison. Antimony, I've told you before, is the main component in gunshot residue. Bismuth. And we'll walk through these electron configs, at least some of them, so you know what you're dealing with. This is going to end in NS2, NP3, third column of the P block. But again, you can have the D and the F in there as well. The D once you hit the 4th period, and the F once you hit the 6th period. And you can see that off your periodic tables that you're going to hit the D once you get to the 4th period here, and the 5th period, and in the 6th and 7th you also have the F block. So you want to be comfortable with that. All right, who thinks they need a little more help with the electron configs?
I'm confused on just if you're like able to keep them
Okay, so you're going to help me write these. You have a periodic table in front of you? You sound wonderful. I'm not so sure you should be talking at all. All right, nitrogen, what's the noble gas that comes before it? Helium is correct. Now, nitrogen is in what period? Second is correct. Is it in the S block? Is it in groups 1 or 2? No, so S block is just groups 1 or 2. So fill that S, you know S can hold 2. After 2S comes okay. If you look at a periodic table, I'm going to put this one right here. Is that showing? Yeah. Can you see that from your seat? All right. So here's nitrogen, absolutely correct in helium. And then here's the second row, so 2. We're not in the S block, so we fill it up, 1, 2. After 2S, there's nothing in between here and here, so we stay 2, and we go to the P block, and this would be 2P1, 2P2, 2P3, and so that's nitrogen, and you don't need a subshell tree. Now for the next one, you're going to walk me through. Here's phosphorus. All the way across up 1, what's your noble gas? Neon is correct. Now phosphorus is in what period? Okay, is it in the S block? So fill it up. Is there anything between the S and the P? No, so we're going to stay with the same number and do 3P, 3P1, 3P2, 3P, and sulfur would be 3P, correct. So this is going to be 3P3. Now for the next row, we've got arsenic. Right here, what's the noble gas? Argon is correct. Now arsenic is in the 4th period. Is it in the S block? No. But now we have to be careful. What's between the S and the P? The D. And the number before D is always 1 less than the row you're in. So after 4S, we have 3, 1 less than that, D, fill her up, and then we're going to go back to 4P, 1, 2, 3. And what you can see here is in each of these cases, and this was Will's question earlier, you've got how many valence electrons, Will?
5.
Correct. All right, keep going. We've got antimony. Krypton. What's between the S and the P? And the number before D is? Correct. So you've got to do 4D10. You can see the D right there. And this is 5P3. They're all going to end in P3 if they're in group 15. They're all going to have 3 unpaired electrons. All right, one more. We've got bismuth, but we're in the 6th period, so we need the F block. So we've got xenon, then what? Now, before we get to D, we got to go through F. The number before F is what? How many less than the row you're in? 2. So this is going to be 4F14, then the D, back to 6P3. You got it. Takes a lot of practice. I would pick a bunch of elements to try and write electron configurations for tonight. That's the only way you get good at it. I had given you on the last classwork 1-4, a whole bunch to write. You should go back and write them in shorthand. All the answers are posted on Edline. So that's group 15, and group 15 is going to have 5 valence electrons, as we indicated. And what you're going to see with group 15, for example, nitrogen, we've got 5 valence electrons, and we want an octet of electrons. 4 is usually the midpoint, so at this point you're going to start to gain. Nitrogen will gain 3 valence electrons to form a nitride ion. And now, if you look at the electron configuration of the ion, you'll have 2 plus 6 will be 8 valence electrons, which is an octet of electrons, and the ion's going to be much more stable than the element, and that's why atoms will lose, gain, or share electrons to achieve that octet of electrons. So the ions typically have a 3- charge, and that's the blank you're looking for in your notes right here. Some of the elements in group 15, like nitrogen and phosphorus, tend to share electrons like carbon does. They'll form covalent compounds. You find that with the nonmetals. Other things you tend to see can be established further with your other groups. Group 16 is your oxygen or chalcogen family. Their electron config ends NS2-NP4. Be careful with going through the D and F block. As we said earlier, the double-digit group numbers for the P block, the back number is the number of valence electrons. Group 16 tends to gain 2 electrons to complete the octet. So this group is going to form ions with a 2- charge, or they will share. And again, you have every variety there, because in group 16, oxygen and sulfur and selenium are nonmetals. Tellurium is a metalloid and polonium is a metal, so you have everything there. I also want to talk briefly about the halogen family. You're going to be doing a lab that involves a lot of substances from group 17. Halogens will combine with metals to form salts. Let's take a look at that. In regard to your halogens, this is group 17. And for example, sodium chloride is table salt. So from group 17 and from group 1, we say, for example, this is an ionic compound, and Cl- is chloride ion, which is one of the halide ions, and your lab will deal with different halide ions. Sodium fluoride is in toothpaste. You also have other salts such as potassium bromide, cesium iodide, etc. So what you find is that group 17 elements combine with metals to generate salts. These are all salts. Some of them you salt your food with, not all. These elements are very reactive. How many valence electrons does an element have from group 17? 7 is correct. So if you considered, for example, fluorine, which is 1s2, 2s2, 2p5, these elements gain 1 electron to form ions. Does the ion now have an octet of electrons? In what shell is that octet? There's the octet. What shell? The second shell. So the ion will have an octet of electrons, and the ion will be more stable than the atom. In group 17, you have your nonmetals, as well as astatine, which is a metalloid, but we're not really going to deal with that one. So for the most part, your nonmetals. Also in group 17, you have all three states of matter, because fluorine and chlorine are gases, bromine's a liquid, and iodine is a solid. So you have everything going on there. The last group of the P block is your noble gas family. These elements are going to end in NS2, NP6. You're going to have 8 valence electrons, and as a result, they already have an octet of electrons except helium, which has a duet. And so these elements are very, very stable. They're of extremely low reactivity. It used to be thought that they were inert. They didn't react with anything, but they do have some reactivity, although very, very low. And when you think about your noble gases, there are many that you're quite familiar with. For example, like at the pizza place, they'll have an open sign, and that'll be neon, that red gas that you see in the open sign. You've been to many parties where you suck the helium out of balloons and you have a very high voice. There's a different gas that actually gives you a very low voice, and we'll talk about that in the next chapter or the one after that. But helium is found in party balloons, and their argon is found in the air, etc. So their noble gases are of very low reactivity because they already have an octet of electrons. Hydrogen is in a class by itself. We place it in group 1. And while hydrogen, like other elements in group 1, has 1 valence electron, what is one difference between hydrogen and all of these other group 1 elements? Hydrogen is a gas, and all the other elements are metals. They're solids, exactly. So hydrogen's really in a class by itself. So your main group elements are your S and your P's. The other classification, if you will, are your transition and inner transition elements, all of which are metals. Your transition metals are in groups 3 through 12. They are D block elements. Their electron configuration ends in D, and most of them have 2 valence electrons, although there are some exceptions. Let's take a look at the D blockers, and let's prove that they typically have 2 valence electrons. For example, let's take a look in regard to your transition elements. We can look at scandium, we can look at zirconium, and we'll look at mercury, for example. So scandium. Who needs help with electron config? You want to just do it? Okay. Oh, question.
You know how you said the group 3 through 12 is in the D block? Couldn't it also be in the F block?
Yeah, that is a little bit murky there. And the way the newer periodic tables are written, it's to help you with your config. So I know what you're thinking right there. If you look at this, before the F block, if you have scandium, you would just have, for example, argon 4s2 3d1, right? Very, very tricky with the F block, because the F block, and I'm going to hit the F block in a sec, this row right here goes right there between lanthanum and hafnium. So if you're writing for lanthanum, you would write xenon 6s2 5d1. If you were writing for this one, or let's do promethium, for example, you'd be here. You would do xenon 6s2, and then we're pretty much just counting 1, 2, 3, 4, 5. So you would do 4f5. So it is a little bit murky there. So the electron config gets murky when you count. You're not going to count these perfectly anymore like you did P1, P2, P3, P4, P5. So it is a little tricky there. I think that's your question. Yes? Yeah, it's a little tricky. And then actually if you wrote it for cerium, you typically would just write xenon 6s2 4f2 when in reality it's actually 4f1 5d1. But that we wouldn't get you on. You would just write it the way you learned. It'd be easier. All right, so for scandium, this one we looked at already. Let's make sure we're good here. We're right here. All the way across up one is argon. And then this is in the fourth period, so we do 4s2, and now it's right here. So what are we going to finish it with? 3d1. The number before d is one less than the row you're in. Valence electrons, you look at highest value of n, which is 4, s and p only, 2 valence electrons. Zirconium, all the way across up one is krypton. And you've got 5s2, 4d2. And again, highest value of n, 2 valence electrons. How would we do mercury? Mercury's right here. We go all the way across up one is xenon. Mercury is in the sixth period, 6s2, 4f14, 5d, 10. And again, highest value of n. Typically, your transition elements have 2 valence electrons. There are a few exceptions to this rule. I'll give you one, but I won't ask you to write it. Silver is kind of funky because it's krypton, 5s1, 4d10. And it helps explain why silver is always 1+. But these are anomalies, and we're not going to play with these this year. But this one would only have 1 valence electron. So if given this configuration, you could see it has 1. Otherwise, I don't think you would guess it. Your transition metals typically have 2 valence electrons. The last piece we alluded to, but let's make sure it's clear. Your inner transition metals fit inside the transition metals. We yanked those groups, we yanked that chain out previously. So lanthanide series, period 6, actinide series, period 7. This is going to make up the F block. And if you look at this on the periodic table, right here after element 57, which is lanthanum, you have this whole series here. This is going to be your 4F, if you will. After actinium, which is right here, you have this chain right here. This is your actinide series. So you have your lanthanide series and your actinide series, and these are the inner transition elements. They make up the F block. They fit inside the transition elements. So your lanthanide series, you've got electrons being added to the 4f orbitals or the 4f subshell. These are very reactive metals. They have very irregular configuration of electrons. In TV sets, they emit light of certain colors. The actinide series are your 5f subshell. These have unstable nuclei, so they're going to have radioactive isotopes for them. But again, be familiar there. And on your periodic tables that I gave you, I believe it's most evident where you've got right here This is your lanthanide series, your 4F. And right here after actinium, you've got your actinide series. This is the 5F, and this is the one where you have all isotopes of these elements are radioactive, right here. All right? So what you've got from today is you should know that the main group elements make up your S, or S and P block make up the main group elements. Your transition elements, that's your D, and then your inner transition elements make up the F. And I had a cutesy little question here that would make you review some of the things we've discussed today. And this is how your quiz is going to be. And you would want to make sure that you could do this. So let's take a minute. It says, write the electron configuration in shorthand for the element in period 4, group 16. So you'll write the shorthand. What is its chemical symbol? How many valence electrons does it have? And what block is it in? I could also ask things like, is it a metal, non-metal, metalloid? Give it a shot. See if you can do it, and that'll be a good close to see whether you understood what we did today. Next time we'll get into periodic trends, which is a little more challenging than what you've seen thus far, but I feel very confident that you'll be good at it. Give it a shot. How'd we do? You ready to check? Not yet?
Yeah.
You ready to check?
Yes.
All right, so only look if you did it, okay? I got this. Did you get what I got? Yeah? Then you're in great shape. Your quiz is going to be like this. The other question I might have asked is for selenium, is it a metal, a metalloid, or a non-metal? Looking at your periodic table, here's your stair-step line. It doesn't touch a horizontal or a vertical. It can't just touch a corner. This is a non-metal. Alrighty? Non-metal.
Good afternoon, Cobras. Just a few minor announcements.
Alright, so
prior
there's your
to
periodic
the
table, and we'll pick up with trends tomorrow.
Our